Okay, let's start. It's my big pleasure to introduce Chen Jiang from Fudan University in Shanghai, and who will speak about minimal log discrepancies for three-dimensional non-canonical singularities.
Okay, thank you very much for the invitation, and it's my pleasure to talk in the ZAC seminar. So it's my first time to talk online. So today I will talk about minimal log discrepancies for the three-dimensional non-canonical singularities, and my talk will be over the complex number C. And so let's say consider X which is a normal say variety. So usually I will assume it's the quasi-projective variety, and then we consider Kx is a Q Cartier divisor. Then so let me recall the basic definition of a terminal singularity or a canonical singularity. So this is actually defined by Reed in early 80s. So if we say that X has terminal singularity, say if we look at its resolution, so say for any resolution of singularities K from Y to X, so this is a resolution of singularity. So we have ky bigger than the pullback of kx. So this I mean by bigger I mean comparing the coefficient of external divisors. External divisors, okay. And we say that X has canonical singularity if we replace this strictly bigger by bigger than or equals to. So so why this kind of singularity is important? So because for the first reason we know that say these are the essential singularities appears in minimal model program. Minimal model program. So for example, we know that there are singularities of minimal or canonical models. So that's the correct singularity we should consider if we want to study minimal model or canonical model of a projective variety. Okay. So let's see what happens in lower dimension. So say in dimension 2, so we know that terminal singularity in dimension 2 is actually smooth. Okay. So actually there's that means there's actually no terminal singularity in dimension 2. So everything is smooth. And for canonical singularity, we know that in dimension 2, it's just the so-called dual singularity, okay, or rational double points. Right? So it's very well understood and very important in the study of surface theory, right? And so then things get a little bit more interesting if we move to dimension 3. So in dimension 3, we know that terminal singularity actually is fully classified. So actually classified by the work of Mori, and later by Collar and Schaffer-Barron. Okay, so for example, let me give you some idea of the some classification. So we know that there are quotient singularities. of type, say 1 over R and A minus A 1, where A and R are co-prime. Okay, so that means it's A3 is a term of the origin of A3 quotient by quotient by cyclic group action with weights A minus A and 1. Okay, and on the other hand, we have also hyperquotient singularity of type say 1 over R A minus A 1 0 and 0. So this notion means that actually we are in a situation of hypersurface in A4 modulo cyclic quotient. So the surface is like this. So the polynomial equation is like this. It's 0. This is in A4 with coordinates x, y, z, and t, modulo this mu the cyclic quotient, cyclic group mu r. Okay. So the weight is just so this is the weight for x, y, z, and t, and this is the weight for f. So this is f. Okay. So basically, for terminal singularities in dimension 3, we have only we have these two types of singularities, and plus finitely many exceptional case. Okay, so this is basically the classification of terminal singularities, and then for canonical singularities. In dimension 3, actually we have no full classification as we can write down the equations in for terminal singularities, but we know it very well. So somehow it's well understood. For example, we can take a crypant blow up to make it terminal, and then the study of canonical singularities is basically the same as the study of terminal singularities, right? But on the other hand, we somehow for the non-canonical singularities, even in dimension 3, we actually we don't know it very well. So the study, so the starting point of my study is to say this talk, or our goal is to understand what happens for non-canonical singularities. So actually, we want to study the difference between this canonical and non-canonical singularities. Say in dimension 3. Okay. So let me move to okay. And the method I'm going to, or the environment I'm going to use is to use so-called minimal log discrepancy. Or MLD for short. Okay, so let me briefly explain what is this MLD. So actually, you can see from the definition of canonical singularity that we measure. I mean, we define the singularity by comparing the coefficient of external dividers. So that is basically also the idea of minimal log discrepancy. So let me move to a slightly generalized setting. So we consider X is a normal variety, and say we have an effective R divisor such that kx plus b is actually R Cartier. So in this case, it is mu R cyclic group of R. Yes, yes. So that is what I mean. Yes. So then we consider say a divisor E, which is a divisor over X. That means it is a is a prime divisor on a birational model of X. So we have so not mu, but say F from X to Y. So this is a birational model, and E on Y is a prime divisor. Then for in this setting, we can define so-called log discrepancy. So which is just defined by the log discrepancy of E with respect to XE is just defined by the multiplicity of E on the KY minus the pullback of KX plus B and plus 1. Okay, so this is the definition of a log discrepancy of E. And the minimal log discrepancy, that means we consider the minimal ones among all such E with some restriction. Okay, so say we fix some Z in X, so say closed subvariety, and we denote this eta Z to be the generic point of Z. Then actually we can define various of minimal log discrepancy with respect to this C. So this is a definition MLD, and I think it's due to Sokolov. So we consider this first we consider LD of Z with respect to this XB. So that means we consider all such E with center contained in Z. So this is the infimum of the discrepancy of E X B, where the center of E in X is contained in Z. Okay. So so on the other hand, we can also consider the MLD of eta Z X B. So then this is just we consider all such E with center exactly equal to Z. Okay, so this A E X, and the center of X of E is exactly Z. Okay, and also so this is if we fix some subvariety, closed subvariety on X, and also we can consider the global version. That means we consider just consider on X. So there's another two I want to mention. So one is the so-called MLD of XB. So if we don't have any Z on it, so then that means we consider all exceptional E over X. So this is A of E, XB, and E is exceptional over X. Or that means center of E is a codimension greater than 1 center. Okay, and also we consider this total log discrepancy. So I should write, yes, this is maybe not standard notation, but then we write this. So then this means we consider all E. Okay, E, and E is just a divisor over X. So that is actually equals to, by my the above definition, equal to this MLDX XB. All right, we just consider all the centers which contains in X. Yeah. Okay. So today mainly I will focus on the global version, this or this. Okay. So we don't fix Z. All right. So actually, so you can see from the definition that actually, so such kind of environment of the pair. So this, So this actually measure how bad the singularity is, right? So this is a very important singularity environment for singularities in minimum model program. Okay. So let me give some remark. Okay. So the first remark is that say we know that, for example, if P in X is a closed point, then actually it's very easy to compute that if say P is smooth point, implies that we can compute easily that MLD of P at X is just a dimension of X. Okay, so actually, the philosophy is that the more singular X is, then the smaller the MLD is. Okay, so and we expect the converse is true too, but this is actually a Shortcroft's conjecture, which is not known yet for dimension at least 4. Okay. So yeah, even in this case, it's very hard. And on the other hand, we also know that some useful remark is that MLD, the value of MLD is always either minus infinity or non-negative real number. Okay. And also, so we can use MLD to define very basic singularities in the binomial geometry. Say, maybe you heard of it, that we have so-called Kalmata log terminal singularity. So this is equivalent to say that, so this is actually definition, that the total log difference of xb is greater than 0. Okay. And also we know that, so this is log canonical singularity is equivalent to say that the total log infinity of xb is bigger, is at least 0. And also equivalent to say that the MLD of xb is at least 0. Okay. So yeah, but actually we are not going to use it in this talk. So let us focus on the definition of canonical and terminal singularity. Then actually you can see that you can translate the definition of read into the MLD case. So we know that X is terminal. Say actually if and only if the MLD of X is greater than 1. Okay, so here if B is 0, then I just ignore it. So I don't write it. So if I write MLDX, that means B is 0. Okay, and then this is canonical if and only if MLD of X is at least 1. Right. So this is very easy, just by definition, right? Because so this is just the calculation of coefficient of exceptional divisors. On the other hand, we know that X is non-canonical. So if and only if this is just by definition that MLD of X is smaller than 1, right? Okay, let me give you some example. So somehow some examples, some easy example, we can calculate the MLD very easy, but in most of cases, MLD is very hard to be calculated. So say let's consider X is just a cone over a curve, over a rational curve. So this is a rational curve of D, and we take its cone, and the singularity, we have one singularity at the vertex. Then we know that actually in this case, MLD of X is just the MLD of X at P, which is just 2 over D. So depends on the degree of the embedding. Okay. And on the other hand, so even for terminal singularities, the MLD is not so easy to calculate actually. So say we consider P in X is a three-dimensional terminal singularity. So we know its classification as I explained in the very beginning, but so we can actually, this is a theorem by Markushevich and Kawamata, that in this case we can calculate that MLD of X at P is say the 1 over sorry, it's 1 plus 1 over RP. So say if P is singular. Okay. So here RP is a Cartier index of Kx. So that means the smallest positive number, positive integer making Kx to be Cartier. Okay. So this is maybe two examples of MLD I want to tell you. So then, what we are going to do is to study the MLD of non-canonical singularity. So actually, by the definition, we know that for non-canonical singularity, its MLD is smaller than 1. But this is definitely not what we want because it's just definition. So we want something deeper than that. So then I should introduce a very deep and very difficult conjecture. So say it's called the ACC for MLD, and which is due to Sokolov. So this conjecture predicts that so the set of MLD actually should satisfy some very nice property, and should the distribution of the set is very nice. So let me explain state the conjecture. So if we fix C, so some positive integer D, and we fix coefficient set, which is DCC set. So that means descending train condition. For example, the standard coefficient set, or just the empty set. Okay. So then the statement says that if we consider the set of MLD of such, so the set of such MLD where the dimension of X is bounded by D, and C is some closed subvariety in X, and the coefficient of B is in this coefficient set. So if we gather all such MLD numbers into one set, then this set is actually ACC. So ascending train condition. Okay. So this is the big conjecture Sokolov predict. So for example, you can see from my two examples above. So in this above examples, I have finite many values, but this 2 over D is satisfies ACC condition, right? So it's only have accumulation point 0, and this 1 plus 1 over R is also ACC set. It has only accumulation point to 1 from above. Sorry, right? Okay, so this is the conjecture predict, and let me briefly explain what is known for this conjecture. So it's known in dimension 2. So this is proved by Alexeyev and Sokolov independently. And it's okay for toric pair. That means we consider X as the toric variety, and B is a torus invariant divisor. So this is by Borisov and Ambro. Okay. So this is basically what we know by now. So it's still open in dimension at least 3. Okay. Although there are some many partial results, but in the full generality is still open. Okay. Okay, so and also why it's so important is because the result of Sokolov, which tells us that this ACC conjecture plus another so lower semi-continuity conjecture, which I will not explain here, implies this is by Sokolov, implies the termination of this. So that makes this conjecture very important. And also, I will explain some other applications for it later. So let's go back to our interest. Okay. So our let's just consider a special case of this conjecture. We want for non-canonical singularity, right? So that means MLD is more than 1. So then I just rephrase this conjecture in a very special case, so which I call this one gap conjecture, which says that this set should be ACC at least in a neighborhood of 1. Okay, so we fix D in positive dimension, positive integer. Then say 1 is not a accumulation point from below of the set, the following set. Say we consider MLD of X, where the dimension of X is at most D. Okay. So that means it is I mean this set is ACC in a neighborhood of 1. So it cannot you cannot accumulate 1 from below. Okay, so you can easily see that this conjecture is a very special case of the ACC for MLD. Okay, so in other words, so we know that I rephrase this conjecture in another form. Say if we fix D in positive integer, then there should exist some positive number. So I know by delta D depend on D, which is positive, such that we have a following condition, such that say if X is say normal Q Gorstein, and dimension X is D. And if we assume that MLD of X is smaller than 1, then we must have a gap that MLD of X is at most 1 minus this delta D, right? So this is what the 1 is not accumulating from below means, right? So and this condition just means that X is non-canonical. So this is basically what the one gap conjecture means. So in other words, that means that so there's a gap between the MLD of canonical singularity and non-canonical singularity, right? So this gap is just denoted by this delta D, which is a positive constant, okay, in any dimension. If we fix the dimension, then there's a gap. Okay. Any question so far?
So far, so good.
Okay, good. Okay, so let's see. So what happens in dimension two? So as a so actually this is theorem or actually easy exercise. I think. So everyone knows surface can do it with dimension is 2. So then actually we can take delta 2 is 1/3. So which means that so if x is a normal surface, normal Q-Grunstein surface, and MLD of x is smaller than 1, that means x has worse than dual singularity, then the MLD of x is at most 2/3. Okay. So and this is actually optimal because we know that equality holds if x is of like quotient singularity of type 1/3, 1, 1. Okay. So this is just a cyclic quotient singularity. Okay. Okay. So then the main theorem just actually tells us the dimension 3 cases. Okay. So this is not known before. Okay. So this is my main theorem. So main theorem, and this is dimension 3 case by myself. Okay. So it says that so there exists some delta 3 which is 3 bigger than 0, such that if x is a normal Q-Grunstein, and if MLD x is smaller than 1, then MLD of x is most 1 minus delta 3. Okay. So this is the main theorem. And let me give some remark, okay, about this value delta 3. So actually, we have some example. So we consider x equals to 1/13, 3, 4, 5. Okay, so this is a I'm writing this means is a cyclic quotient of order 13 with weights 3, 4, and 5. So then it's actually easy to calculate the MLD of x is equal to 12/13. So you just add these 3 numbers together to get 12, and actually you can see that it is in the minimal log difference. So which means that actually delta 3 should be smaller than 1/13, right? Termination of ellipse implies it is no. It's the converse is not true. So that's bad news. Because we know termination of ellipse in dimension 3, but we don't know ACC for MLD in dimension 3. Okay. So so actually so we can take delta equals to 3. Delta 3 equals to 1/13. So this is a result of Jihao Liu and Xiao. So which says that we can take delta 3 equals to 1/13 in main theorem. Okay. So this is proved by some computer program. So actually in my paper I gave some algorithm which allow us to calculate this delta 3 very explicitly. And Liu and Xiao they use some other they analyze my algorithm, and then they use computer to calculate. So which eventually after some hard working, eventually they get this delta 3 is actually 1/13. Okay. So and which means that this 1/13 is also optimal. Okay. So let me explain briefly what the idea of the proof. Okay. So actually, the idea is what's your actually I don't know the correct number. Sorry, I don't know the correct number in dimension 4. Maybe 200 or something. I guess. Yeah, but I expect the gap will appear in the quotient singularity case. So if you can calculate the gap of the quotient singularity, then you can get actually the gap for all MLDs. This is only my expectation, but I don't know if it's true or not. Okay, at least in dimension 2 and 3, it's okay. Okay, so the idea of the proof actually is very one simple idea is just we do the classification. Okay, so let me briefly recall. So recall that the classification of terminal singularity. So if we have x is terminal 3, 4, then actually this is done by Mori. So we have some. Let me just write this. We have a black box, which maybe I should call it a Morris game. So then after this game, we get the classification. And actually, we have a full list of terminal singularities in dimension 3, right? So then the situation here is actually now we have x is 3, 4. So here means MLD x is bigger than 1, right? And here we have MLD of x is bigger than 1 minus delta, where delta is, we can take it very small, but bigger than 0. Then actually what we want is we just, we use our setting to, we apply Morris game in our setting, but we use modified version, okay? Then still we get our classification. So main theorem holds for 1/13. Yes, correct. Yes, that's Liu Xiao's result. So I get my classification, and we can check that eventually we get MLD. In the classification, the MLD is at least 1. Okay, so that means canonical. And we're done, right? So what we need to do is just we classify all such 3, 4 singularities with MLD bigger than 1 minus delta. And we, after the classification, we prove that it is canonical. Then we're done. Okay. So this is just I mean the very basic idea. Okay. So here we just use we mainly use toric method and combinatoric information. Oh, sorry. Combinatoric method information. Okay. So
small question. Small
mm-hmm.
question.
Is there? You mean Yoshinori's question?
Yeah.
Actually, I don't know any non-quotient example. I think if you do it carefully, then maybe 1/13, 3, 4, 5 is the only example with with MLD 12/13. This is my guess. I didn't check it very carefully, but I believe so. So that means the quotient singularity. That example I gave maybe the best singularity smaller with MLD smaller than 1. I guess. So this is my expectation. Okay. Oh, okay. So let me move on to this. So let me just explain the key step. Actually, it's also the key step in Morris proof. Okay, the key step is to classify all hyper quotient singularity with MLD x bigger than 1 minus theta, right? So the setting is as the following. So we have x equals to f equals to 0. So this is hypersurface in A4, but quotient by a cyclic group of order R. Okay, and this of type 1 over R, A, B, C, D, and E. So this weight corresponds to the weight acting on X, Y, Z, T, and F. Okay, so then the key step is actually we want some equation on this information A, B, C, D, E, and R. So this is we want to show that for any k between 1 and R, we have this equation like AK plus BK plus CK plus DK is equal to E plus R plus K. Okay, and here AK is just the residue of AK modulo R. Okay, so I mean I here write the residue. Okay, so that means if you consider the residue of AK, BK, CK, DK, and EK, then they form this very nice equation. So once you have this equation, you can use the so-called terminal lemma to determine the pattern of A, B, C, D, E, and F and R, and then after the classification, you can get very nice. You can get the full list of the possibilities. Okay, so this is one of the central step in Morris proof, and so the point is that roughly. So usually Q-Grunstein three-dimensional singularity is not cyclic quotient, not only cyclic quotient and hyperquotient singularity. So if it's getting worse, I mean the singularity is like chaotic singularities, then it becomes worse and not always hyperquotient. So this is not true. But in my case, I can reduce to this case. I mean, I can always assume X is a hyperquotient singularity because its MLD is not so small. Okay? So then, if this star holds, so that means we are actually in the Morris situation. So we can use Morris game, and then this induces that actually X is terminal. So maybe I cannot explain in the full detail, but if you run Morris game, then exactly you get Morris list, and the list is terminal. Okay, and say if this delta fails, then actually we consider also this this information is MLDX bigger than 1 minus delta. Then that means we can we get into the other situation is that we have a artificially constructed singularity. we construct W. W is just the quotient singularity of R of type 1 over R, A and B and C and D and minus E. So this is a 5-dimensional cyclic quotient. How do you reduce to quotient of hypersurface? So that so we can take the cyclic. I mean, take the index 1 cover of X. So that means that makes X to become a cyclic quotient of canonical singularities, and then we can rule out the non-CDV point. So that means X. So if it is non-CDV point, then it is very easy. So then we reduce to the case that X is a cyclic quotient of a CDV point, and the CDV point is just a hypersurface in A4. So that is by clarification. So then we reduce to this case that X is the quotient of hypersurface. Okay. Okay. So then we artificially we construct this 5-dimensional quotient singularity, and actually by these two conditions, we can calculate that MLD of this W. Then we know that this W is smaller than 2, but bigger than 2 over delta. So this is some this follows by the combinatoric information. But this fails. I mean, this violates the toric ACC. Okay, because in this case, W is cyclic quotient, so W becomes toric, and so if delta is very small, then the toric ACC tells us the MLD of W cannot accumulate to 2, so there must be one gap. So then we conclude the proof. Okay, so this is basically what I want to say about proof. So the last case is one of the most interesting case. We reduce it to 5-dimensional cyclic quotient singularity, and we use toric ACC to get a contradiction. Okay. Okay. So let me talk about some application. Say to Calabi-Yau varieties. So it's somehow surprising that this local statement can have some application to this global Calabi-Yau, the global geometry as Calabi-Yau varieties. So let me recall the definition. So say X is a normal projective. Then X is Calabi-Yau if and only if Kx is numerically trivial. Okay. So then we consider the global index of X is just the minimal M in the positive number such that M Kx is actually linearly trivial. Okay. So then the expectation is that actually such kind of global index should be bounded if we fix the dimension. Okay. Of Calabi-Yau bounded. So actually, I should allow mild singularity, not so bad singularity. So actually, there's a conjecture which we refer to as index conjecture. So this is due to Shokloff again, saying that this should be true. Okay, so say if we fix D and P in positive numbers, And then there exists some m, depends only on for the existence. Yes, we need the semi-log canonical. So this is the result of Gongyu. Yes, yes, we need at least semi-log canonical. Yeah, you are right. So M depends only on this P and D, which is positive integer, such that if we consider pair XB, which is LC or semi-log canonical pair. Yeah, LC or semi-log canonical is enough of dimension D. And we consider pair is Calabi-Yau, so pair is numerical trivial. And we consider PB is a weight divisor. So that means the coefficient of B is not so bad. It's like something over P. Then we know that this MKX plus B is numerical is linearly trivial as a divisor. Okay, so this can be viewed as a effective abundance, right? Right. So the existence of M for every X is proved by Gongyu. Okay? But what we want is to get a uniform M. Just depends on the dimension and the coefficient of B. Okay. So this conjecture. So let me summarize what we know. So actually, I have a remark about the difficulty of this conjecture. So actually, the more singular, more singular X is, I think the easier this conjecture is. So smooth case, actually smooth case is most difficult, I think, bigger than singular case. Singular. And of course, if B is zero case is bigger than B is non-zero case, right? So because if B is non-zero, that means it's more singular. Okay. So actually, I think the most difficult part of this conjecture is just the smooth case. That means like Calabi-Yau manifold case. So this non case. So let me say in dimension 2. In dimension 2, actually, this has been studied like in 80s. So we know that if B is 0 and X is KLT, then we can take MK is 0 for some M at most 21. So this is by classification result. So this is by Blach and Deqi Zhang. So they study such kind of say so-called log unicorn circuits. I mean they actually they have some classification result on this. Okay. So then in its full generality, it's actually proved by Yening Xu. So this is in journal. In journal is okay by a result of Xu. So the student of Birka. Is 12 enough? Actually, I'm not sure. So smooth case 12 is enough, but singular case I'm not sure. So as far as I can remember, so their result says 21. Okay. So in general, I mean SLC case. Okay. It's by Yening Xu. And let's move to dimension 3 case. The dimension 3 case actually we know it if B is 0 and X has canonical similarity. Then this is okay. So MKX is numerical is linearly trivial. So if we can take m to be this number. So 2 over 2 to the 5, 3 to the 2, 5 to the 2. Oh, sorry, this is maybe 3. And 7, 11, 13, 17, 19. So if you multiply all these numbers together, it's okay. Okay, so this is the result of Kawamata and Morrison and Oguiso. Okay, so actually Oguiso proved that this number is optimal. I mean, if you want to get a uniform M for all MK to be linear trivial. Right. Yeah. Beauville. Yeah, actually, this number is called the Beauville number. Okay, or Beauville's number. Okay, thank you. Okay, so then what happens to my result is that we can deal with non-canonical case. Okay, so we know that B is 0 and X is KLT case. So if it's non-canonical but KLT, I can treat it. Okay, so this is okay by main results. That's there, but not directly. So we need to prove something. But maybe I will not explain here. Okay, and later on, so Ye Ningshu also showed LC case. So X B is LC, then this is okay. I mean in dimension 3, by Ye Ningshu. Okay. And so later on, we show that this is okay for SLC. That means in dimension 3, in its full generality, so it's okay by a result of myself and Haidong Liu. Okay. Is effective M known? Yeah, actually that's a good question. So actually in here no effective out. Okay. So yeah, all of this result I'm saying is in dimension 3. But for chaotic case, I'm very happy if we can get any effective results for this M. But unfortunately, so far, no. But my expectation is that the Beauville number should be okay, because as I explained, the more singular the variety is, then actually the smaller the M could be, I think. Yeah, so this is my expectation. Okay, so so yeah, actually I think I will just stop here. And any questions?
Okay, thank you very much, Chen. Thank you very much. Let's clap. Thank you very much. And yeah, any questions? Oh, there's some questions in the chat.
Okay. Florian asked, how does it follow from the local result? That's actually a long story, but what I can show is that if B is, say, if B is 0 and X is non-canonical, KLT Calabi-Yau, then actually what I can show is that this set of X is bounded. I should say bounded modulo flops. So that means if we allow some flop on X, then eventually X it goes to a bounded family. And in that case, the bounded family case, we can bound the global index, and then we can pass the boundedness to the original X. I mean, because they're only flops. So this is the key point. But to prove the boundedness, we need more effort. Maybe I could not explain in 1 or 2 words. Non-KLT case is smaller than KLT. I think that depends on the LC case. So LC threefold is implied by SLC surface case, right? In that case, SLC surface case, I'm not sure if there's effective. Maybe there is some effective number, but I'm not sure. Sorry.
Okay. Oh, there are a lot of more questions.
Sorry, can I ask?
Yeah, Jürgen, please ask.
I don't understand your reduction on my theorem to the hyperquotient case. Some few words about this. Yes, this one. Yes.
The reduction to hyperquotient.
Yeah.
So we just the first step is we take a we take a index one cover of X.
Okay.
And then the cover becomes canonical.
Mm-hmm.
And if it is non-dual, it's not the CDV singularity, then it's easy because we can actually show that in this case the MLD of X is smaller than 1 over 2. So just by some like calculate the ramification, so we can get that the MLD of X is smaller than 1 over 2. So that the remaining case is just the quotient by CDV singularity.
Okay, but does it work in any dimension? This step, I mean.
No, because in higher dimension we don't know if like something like CDV singularity is a hypersurface. Such kind of result is not known. Yeah, if it's known, then I mean might be okay for higher dimension. But I actually I don't expect this to be true. Yeah, but I think what could be true is my result, my method could work for all hyperquotient singularities. So that might be true after some modification, I guess. But of course, not all singularities are hyperquotient singularities. So we cannot work on it. I mean, as in dimension 3. Yeah, this is my understanding.
Okay, there are more questions in the chat.
Yeah, let me go one by one. So Alexander asked, where is there a geometric connection between non-canonical singularities and the corresponding target singularities? Actually, I don't know. I mean, I read the toric singularities by the combinatory information of this quotient. So I don't know any. Sorry, I don't know any connection between. So the non-canonical singularity is dimension 3, but the corresponding toric singularity is in dimension 5. So I'm not sure how it can be related very natural. So if there's real geometric relation, maybe then it's possible to generalize it to higher dimension. Yeah, and then it helps us to understand the ACC for MLD well, I think. Yeah, so maybe that's what I should think about next. Yeah, thank you. Okay, and Florian asked, you mean non-KLT Calabi-Yau modular flow are bounded? Yeah, so that's one of my results. I didn't explain today, but I can show that non-canonical KLT Calabi-Yau threefold. So non-canonical KLT Calabi-Yau threefold are bounded modular flow. Yeah, this is one of my query. Yes. And Chunhui asked, for the MLDX of curves, For curves, because we only look at normal curves, so that everything is smooth. So MLD always equals to the dimension. That is 1. Yeah. So I think in
Okay, one more questions in the chat. Yeah.
If B is not equal to 0, what can be M such that this is let me see. So in this case, mainly we use boundedness result. So everything is not effective. But say, for example, if X is smooth, and so if we are lucky that X has no torsion line bundle, then every M make it well divider can make it linearly equivalent to 0. So this is the best we can have. But in general, it becomes very complicated, I think. Yeah.
Okay. Yeah. If there are no more questions, let's thank Chen again. Let's clap. Yeah.
Okay, thank you very much.
Thank you very much. And okay, so
thank you.
Thank you. So see you on Thursday.
Thank you for coming.
Yeah.
Okay.
We'll upload the video today later. So, bye.
Bye.
Bye, everyone. Bye.